Our next speaker is Nurcan Durak, who is a postdoc at Sandia Labs in Livermore. You may not know there was a Sandia Labs in Livermore. She obtained her PhD from the University of Louisville. She's been talking about coronal loop detection from solar images.
Good afternoon. Today I'm going to talk about coronal loop detection. We went to astronomy and astrophysics fields again. First, I want to describe what is coronal loop. I think it is not very visible from the back seats, but here there is one loop and there is top parts too. And coronal loops appear on the solar surface, and they are the immense arches of hot gas, and they are related to other events like coronal heating problems, solar flare triggering, and abrupt temperature changes. And astrophysicists analyze these coronal loops to understand their features and understand the relations between the other solar events. Okay. And in order to make scientific analysis, they are analyzing SOHO EIT images. And SOHO has been taking pictures of the sun since 1995, and it takes 6 pictures per day mostly. And it is taking the pictures in different ultraviolet wavelengths. We are doing our analysis with the 171 angstrom images. Currently, astrophysicists are looking at every image separately, and if they find interesting coronal loops, they are just marking that region on the image, and they are putting that image into their interesting data sets. And it is very time-consuming, and it is subject to human errors. In our study, we want to automatize this detection phase. Here, SOHO is taking images of the sun, and NASA is storing those images in SOHO EIT catalog, and we are getting those catalogs, and we are learning features, and learning coronal loops, then delivering just subset of solar images with coronal loops to the researchers. I want to show 2 samples with coronal loop and with coronal loop and without coronal loop. And in this study, we are interested in the coronal loop's outer surface, not inside the disk, so just outside the disk. And it is not very visible, but there is some loop shape here. And in the other one, there is no coronal loops. But there are some other activities, as you can see. So we have to distinguish those activities from coronal loops. We have lots of challenges in this project. First thing, all the coronal loops are in different shape, in different sizes, and their density is changing. For example, here, density is very high here, but it is losing intensity in this part, and we are using lots of data. When we apply image cleaning techniques, we are, for example, in the last one, nothing is left after image cleaning. And coronal loops are not the only events, so there are other solar events, and those events share some characteristics with coronal loops. So we have to learn coronal loops, but we have to learn other events, and we have to make distinction between those events. Another challenge is coronal loops are embedded in bright regions, and we have to bring out those coronal loops from those regions. And as I said before, densities are changing. In the top parts, density is very low, so when we apply image cleaning, we are losing information from top, and every information is important for researchers. And there is time dimension of this data. It has there are solar cycles, and there are two main solar cycles, solar maxima and solar minima. And in solar maxima, there are so many coronal loops, but there are so many other events too. Here, in 2001, it is the highest. It is the solar maxima, and currently in 2012, we are also in solar maxima. So there are so many events occurring in the sun. And in the solar minima, there are not many events. So if we train our system based on solar maxima, we will miss the images without loops. We have to learn from those images without loops too. I want to show one example here. This is the quartz sun. There are not many activities, and the other one is from 2002. This from solar maxima. You can see many events. To solve the problem, we are applying classical pattern recognition problem. First, experts are marking the images with coronal loops, and they are locating those regions. After that, we are preparing images. We apply several image cleaning techniques in this phase, and we are extracting blocks around the sun, around the solar disk, and we label those blocks as loop or non-loop. Then from those two categories, we extract features and we train. We train several classifiers. Then we get classifier models at the end. Here, those yellow boxes are the expert markings, and the other red ones are non-loop regions. So we have to distinguish those two types. And maybe you can see here there is no like arch shape or anything, it's just a cloud. First thing, the image was very problematic, and first we are applying some RDL software to remove some instrument defects. Maybe you can see some grids in the image. We are getting rid of those grids, and there are also some noise. We also get rid of those noise with RDL solar software. After that, we apply the speckling and smoothing to remove specks, and we apply wavelet transform to get much smoother image. Then in the last phase, we do background subtraction to bring out coronal loops from the brighter regions. Then we are working with those final images. See, the coronal loops are clear. After that, as I said before, we are extracting blocks around the solar disk. Here you can see the blocks over there. And there are some positive classes and negative classes. First, we have some gray level images, and those gray level images are important for us, but we also want to get contours, just the skeleton of those fluxes. So we apply some skeleton technique we implemented. And here you can see we got the skeleton very well, and the other like morphological technique was not very successful. It ended up changing the shape, so it's damaged. And after that, we have to receive each contour separately. Here there are so many contours, and there is one loop contour here, and there are two non-loop contours, and there is another loop contour there. So we have to get all the contours and classify those contours like loop and non-loop. Here we have lots of problems. As I said before, the top parts are missing, so this part is missing. How am I going to connect this part with this part? Even we can merge those two separate contours and we can make one group, but it is very hard for automated systems. So I developed one salient contour group extraction method, and here I am using some perceptual rules, and I am using Markovian macro random fields here. I'm not going to talk about that. After that, we have gray level blocks and the binary blocks. And from each one, we are extracting features. We are extracting statistical features like brightness, contrast, and we are like histogram of oriented gradients, directional derivatives, eigenvalue histograms, and curvature histograms. And from binary version, we are getting half-based features like ellipse. We are fitting ellipse to the contours, or we are fitting line on the contours. Also, like we are using arc to chord features. Then we trained several classifiers: AdaBoost, naive Bayes, decision trees, k-nearest neighbor, multi-layer perceptron, and in the first phase we were not receiving very good results. The highest result was like 67%, and since the time is important, we had to select the training data very carefully. We didn't have lots of expert markings, so we selected 30 images from each, like 1996, 1997, they are solar minima years, and 2000 and 2001 solar maxima, and 2004 and 2005 is like median, not like minima, not like maxima. And we received 400 loop blocks and almost 8,000 non-loop blocks. So there is imbalanced data problem there. It is like 1 to 20. And these are the results of tenfold cross-validation. For us, both precision and recall were important, so they should both high. And AdaBoost with a decision tree gave the highest result for us. Since we didn't have lots of positive instances, we decided to do incremental learning. So we had some images, we downloaded images, then we applied the classifier models we obtained in the previous phase. Then based on those classifier models results, we trained the data again. Here there are two types of results. One of them is like positive results with high confidence. So we trust them and we put them into training data automatically. But there are other types, they are like with low confidence. So classifiers didn't agree on those instances. In those ones, we showed them to experts. So experts gave feedback on those. Then we put them on the training data again. With that phase, we increased the number of loop blocks to twice almost. And non-loop blocks we didn't add too much, just the critical non-loop blocks to increase the diversity in the training data. And with that, we increased the training and tested. We increased the training results. But we were very conservative. We didn't want to add bad, like improve the precision, but decrease the recall. So they should be both good. And based on those classifier models, we implemented solar loop mining tool. And this tool, astrophysicists enter a set of images. Then our tool separates them into two groups, like groups with loops and groups without loops. And generally it takes 3 seconds per image, all the image preparation and the training. And we also tested this tool. We had 100 images from different years. and 50 of them had loops and 50 of them didn't have loops, and we were able to discriminate these images with high confidence, high precision and recall. Here we also developed a web-based image query tool, and in this tool researchers are just uploading the images, and they can query on the database. I just presented one portion, first phase of the our study, and it was a new problem, new pattern recognition problem, and we had to deal with like imbalanced data or limited training data, and some experts were giving training data for us, but there were like a couple of students, PhD students, and everybody has marking different region, so there was no consensus between them, and that decreased our classification results. Also, we had dynamic nature of the data. Let's say we trained the data with certain years, but if you give 2012 images, what's gonna happen? So we wanted to provide diverse training data to improve the confidence of our system. And I would like to thank John Schmaz from the University of Memphis, and some like Marcus Eschwanen from Lockheed Martin. They gave good comments to us. Thanks so much.
Our next speaker is Nurcan Durak, who is a postdoc at Sandia Labs in Livermore. You may not know there was a Sandia Labs in Livermore. She obtained her PhD from the University of Louisville. She's been talking about coronal loop detection from solar images.
On the solar surface, and they are the immense arches of hot gas, and they are related to other events like coronal heating problems, solar flare triggering, and abrupt temperature changes. And astrophysicists analyze these coronal loops. First, I want to describe what is coronal loop. I think it is not very visible from the back seats, but here there is one loop and there is top parts too. And coronal loops appear to understand their features and understand the relations between the other solar events. Okay. Good afternoon. Today I'm going to talk about coronal loop detection. We went to astronomy and astrophysics fields again.